All right, Chemistry 1411. We're still working on practice exam 4 here. This is question 27. If the measured voltage of the cell that's shown here, zinc solid, gives you or gets oxidized to zinc 2 plus and silver plus gets reduced to silver in the solid phase, we have an E cell of 1.37 volts. When the concentration of the zinc 2 plus ion is 0.01 molar, what is the silver plus concentration? Well, we've got our cell, our galvanic cell, which is zinc in the solid phase. Then we have zinc 2 plus ions in the aqueous phase, separated by a salt bridge. We've got silver ions in the aqueous phase that get reduced to silver solid. This is our anode over here. Anode is where oxidation occurs. This is our cathode, where reduction occurs. And I went ahead and looked up the standard reduction potential for the zinc 2 plus ion, and I get negative 0.7618 volts. I did the same thing for the silver, and I get that my standard reduction potential for silver is 0.7996 volts. And so I can calculate the standard cell potential, E naught cell, which is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. And when I do that, I get the E naught cell is equal to 0.7996 volts, subtract negative 0.7618 volts. I get the E naught cell is equal to 1.56 volts. Now that I have my E naught cell, I could plug that into this formula, which is E, which has been given to me, which was 1.37 volts. This is my E at non-standard conditions, is equal to E naught subtract 0.0257 volts divided by N multiplied by the ln of Q. Well, how many electrons are being transferred in this reaction? I'm just going to write it on the side that if we have zinc plus silver plus ions producing zinc 2 plus ions plus solid silver, in order to balance that, I need to put a 2 in front of both of my silvers, and I can see that overall the zinc is losing 2 electrons and the silver overall is gaining 2 electrons, and so my N is equal to 2. So now I know what my N is. How am I going to calculate my Q? Well, I know that the ions are in aqueous solution, so I have zinc 2 plus, which is an aqueous ion, and I have the silver, which is an aqueous ion. I'm not going to include the zinc and the silver here because those are both solids. And so my Q is going to be equal to the concentration of the zinc 2 plus ions divided by the concentration of the silver plus ions squared. Now I can plug some numbers into my formula, can't I? I can say that my E, which was 1.37 volts, is equal to the standard cell potential, 1.56 volts, subtract 0.0257 volts divided by 2 times the ln of Q, which is going to be equal to 0.010 divided by x squared, like that. Now all I have to do is solve for x, don't I? So I'm going to simplify this to 0.01285 multiplied by the ln of 0.010 divided by x squared is equal to 0.19 volts. Then I can say that the ln of 0.010 divided by x squared is equal to 14.79. Then I can say that 0.010 over x squared is equal to e to the power of 14.79, which is equal to 2.64 times 10 to the power of 6. Then I get the x is going to be equal to the square root of 0.010 divided by 2.64 times 10 to the power of 6. So I get the x, which is equal to the concentration of my silver ions, is equal to 6.2 times 10 to the power of negative 5 in its concentration, so it must be moles per liter. And the answer is B, 6.2 times 10 to the negative 5 molar. Question 28, calculate the cell electromotive force for the following reaction. So that just means the E cell for this reaction. So I'm at non-standard conditions because the concentration of my copper is 0.1 molar, and I need to figure out what the concentration of my H plus ions are, and I can figure that out from pH. Let's rewrite the equation. So we have copper 2 plus, which is 0.10 molar, plus hydrogen, which has a pressure of 1 atmosphere, produces solid copper, plus 2H plus, which is aqueous. And since the pH is equal to 3.00, I can say that the concentration of H plus is equal to 10 to the negative 3.00. The concentration of my H plus is equal to 1.0 times 10 to the negative 3 molar. So now I have the concentration of my H plus. I'm going to need to calculate Q for this reaction because I'm going to plug that into my formula to find the non-standard cell potential. Let's work out the Q first. So Q is going to be equal to the concentration of H plus ions squared divided by the concentration of copper 2 plus ions multiplied by the pressure of H2, which is 1.0 times 10 to the negative 3 squared divided by 0.10 multiplied by 1, and I get that my Q is equal to 1.0 times 10 to the negative 5. Good enough. Now, how many electrons are being transferred in this process? Well, I can see that as I go from copper 2 plus to copper 2, I have to gain 2 electrons. And as I go from H2 to 2H plus, since I have 2 positive charges, I had to lose 2 electrons. So I know that my N is equal to 2. Now I need to find my E naught cell. Well, I know that the copper and the hydrogen, I can look up their standard reduction potentials. So I look up the copper 2 plus, so copper 2 plus 2 electrons produces copper in the solid phase. My standard reduction potential is 0.34 volts. Copper is also my cathode, and I can tell that because the copper is undergoing reduction. So this is my cathode. The hydrogen is undergoing oxidation. So H2 gets oxidized to 2H plus 2 electrons. That's the standard hydrogen electrode. So its standard reduction potential is 0. I know I have it written as oxidation, but it wouldn't matter which way you wrote it. It's still 0 volts. 0 volts is 0 either way. So I get my E naught cell is going to be equal to the standard reduction potential of my cathode, subtract the standard reduction potential of my anode. It's going to be equal to 0.34 volts minus 0 volts. So the standard cell potential is 0.34 volts. Now I have everything that I need to determine my E cell, because I'm going to use the formula that E is equal to E naught cell subtract 0.0257 volts divided by N multiplied by the ln of Q. And we have everything we need. So we can say that E is equal to 0.34 volts subtract 0.0257 volts divided by 2 multiplied by the ln of 1.0 times 10 to the negative 5. When I punch that into my calculator, I get 0.34 volts subtract negative 0.15 volts, and I get that my cell potential is 0.49 volts, which is B. Question 29, what current is needed to deposit 0.5 grams of chromium metal from a solution of chromium-3 ions over a period of 1 hour? Well, I know that chromium, my chromium-3 plus, is being reduced by 3 electrons to make chromium metal. So that means for every 1 mole of chromium that I make, I need to have 3 moles of electrons to produce the chromium-3 ions. I also know that current is equal to the amount of charge per second, and since I have 1 hour, I'm doing it over 3,600 seconds, right? 60 seconds in a minute, 60 minutes, 60 times seconds, 60 times 60 gives you 3,600 seconds. So let's figure out how much current is required by determining the amount of charge, and then we'll just divide by 3,600 seconds. So let's do some dimensional analysis. If I have 0.500 grams of chromium, I know that in 1 mole of chromium, I have 52.0 grams of chromium. If I was to stop here, grams of chromium cancel. But I know that for every 1 mole of chromium that I want to produce, I need 3 moles of electrons, don't I? This cancels out the number of moles of chromium. And I know from Faraday's constant that for every 1 mole of electrons, I have a total charge of 96,500 coulombs. This cancels out the number of moles of electron and gives me the total amount of charge required, which is 2,738.6. I know I'm carrying too many sig figs, but that's neither here nor there. So in order for me to determine the amount of current required, the current is going to be equal to my 2,738.6 coulombs divided by 3,600 seconds, the amount of time, and I end up with 0.773 amperes, because an ampere is equal to a coulomb over second. Question 30 for the electrochemical cell shown here. Nickel solid and nickel 2 plus 1 molar, hydrogen ions with a concentration of 1 molar, hydrogen gas with a pressure of 1 atmosphere, and platinum electrode. Which one of the following changes will cause a decrease in the cell voltage? Well, if I take a look at the reaction that's occurring here, I have nickel in the solid phase plus hydrogen ions, which are aqueous. I'm oxidizing the nickel to nickel 2 plus ions, and I'm reducing the hydrogen to H2 gas. I need to balance out this equation, so I'll put a 2 here. I have a concentration of 1 molar for my hydrogen ions. I have a concentration of 1 molar for my nickel ions, and I have a pressure of 1 atmosphere for my hydrogen gas. Now it's asking me for which one of these changes is going to cause a decrease in the cell voltage. Remember, if the reaction is spontaneous in this direction, that the E cell is going to be positive. So if I want the reaction to go in the reverse direction, my E cell would be negative. Let's take a look at the possible answers. We'll start with A. If we decrease the nickel 2 plus concentration, if I decrease the concentration of the nickel, that's going to be removing a product, which is going to push the reaction towards the products. So that is going to increase the cell voltage, not decrease it. It's going to make it more spontaneous in the direction written. None of the above. We'll move on from there. The next one is increase the pressure of the hydrogen to 2 atmospheres. So if I increase the pressure of the H2, it's going to push the reaction in reverse, which is going to cause a decrease in the E cell of the reaction. So the answer is C. If we increase the amount of hydrogen, it's going to push the reaction in the reverse direction, cause it to be less spontaneous in the direction that it's written, and it's going to cause a decrease in the cell voltage. So the answer is C. If we were to lower the pH, that would mean that we were increasing the concentration of H+, and so that would push the reaction towards the products, make it more spontaneous, increase the E cell. And then if we were to decrease the mass of the nickel electrode, that doesn't affect the equilibrium because nickel is a solid.